work a little bit. It took me a really long time to just get through question 2, and I couldn't get started on it yesterday because I was busy all day after class. So
Yes. So yesterday's homework was well, challenging, and I really expected you to sort of get a good head start, but I did not expect everyone to finish it. I will go over it today, and I will assign you homework, hopefully not as hard. But I will reopen the submission, so I want you to finish it, even though I'll explain it today. I want you to finish it, on your own, to just commit it to memory, better understand it, and then yes, I will let you submit it until tomorrow. So I'll have both homeworks open until then. Sorry. Okay. Well, let me turn my camera on. So let's. Yeah, sorry, I have allergies, but excuse me. Let me turn off the light so that it doesn't. All right. Okay. Other questions? So I'm almost done grading the exam, right? So in the summer there are no TAs, no graders, but I'm almost done grading the exam. So don't worry about that. I'm going to go over the homework now. We're going to introduce some new stuff today. Before I go over the homework, let's look at the course outline. So those homeworks are not assigned yet, but they will be. Let's refresh this. Let's see. We've covered the 5-variable K-map. I'll go over the homework, so it'll be additional coverage of that. Then we're going to start a new topic, right? So the way I will introduce it, I'll answer a question in a second, is going to be through a 7-segment display. But in the textbook, the corresponding subchapter is the don't care conditions. So that's a big thing. Then we'll go into Quine-McCloskey tabulation or tabular method, and then related to it is the prime implicant table, right? So those are not covered in the textbook at all, and I'll give you a couple of external readings for those, right? So that's the plan going into the next week, and then after that, in fact, maybe on the 28th, I might be able to start what is effectively in the book covered in chapter 4. So that's the plan. I heard a raised hand, so there is a question. Go ahead.
Hi, Professor. This is Thomas. I wanted to know if you could reopen the submission for homework 12 because I had some problem uploading it just now.
Homework 12 is the one assigned today. Yes. You probably just came in. Yes, I said that I will reopen it.
Okay.
Yeah, because I didn't expect everyone to finish it. It was a lot, and it was difficult, right?
Yeah.
Because you only very quickly introduced 5-variable K-map. So I'm actually going to go over it now, which is part of the teaching process. But you should still finish it, even though based on my explanation, and then I will have the submission open until tomorrow. But there will be new homework too. Okay.
Okay. Thank you.
Sure. Excuse me. So let's go to the lecture. Not this one. Let's go to what's happening? Or is it this one? Sorry, just yeah, very good. This is it. Actually, sorry, because I have to keep blowing my nose, I'm going to turn off my camera. I don't want you to see that. Okay. So I'm sure the quiz yesterday was easy. If I'm not going to go over it now, but if you want me to go over it later today, I probably will have time, and if you want me, I'll do it. But it's sort of like the same as the previous homework. So I'm going to skip it now. It's not so easy. This is actually a quiz from previous semester. It's same topic, but it would probably take the same amount of time to go over it. Oh boy. Okay, sorry. That is just taking too long. Okay, let's go straight on that. Technology. We still haven't figured out how to skip to the end of the slide in presentation mode. All right. So this was the first problem for today. So this was the less difficult one. So I'm hoping that everybody did this one. And here we have a function with only 3 variables, right? And we have a sum of products representing it. It's a standard form, but not canonical because only one of these products is a minterm, right? So A, B, C, A prime, B, C prime. The other ones are terms that are already implicants, right? Meaning that the last one will only produce a single one on the K-map, but the other 2 will produce more. Can somebody just quickly tell me how many ones will each of these first 3 products produce?
4.
Each one of them. Like, for example, A prime, B prime. How many ones does that make?
2.
2. Yeah, very good, right? So, if you start with all 3 variables, which is minterm, which is always makes a single one, and then if you take away a variable, like you're doing all 3 of these, that'll make 1 more, and I mean, not 1 more, twice as many, 2. And then, if we had like a single literal like B prime, right, that would produce 4 ones on the map, yeah. Anyway, so there we go. So let's put them on the map, right? If we do, first we'll put the dimensions. A, B, A prime, B prime, C in the middle, C prime on the sides. Notice that we're not naming our variables X, Y, Z, T, they're A, B, C, D. So we're going to use the X, Y, Z, and T or whatever to name our prime implicants. And again, what I just said before is that all 3 first, the first 3 terms in the sum, they are implicants, right? Because they imply more than one on this map, but we don't know if they're prime or not, right? Anyway, so A prime, B prime. So we have A prime, B prime. As Anna said, it will produce 2 ones that will go there. Okay. Then we have A C prime. So A, then C prime. Right. Right. So we have A is this half, and then if this is C, then this is C prime, right? 2 ones. Now, but this is also C prime. Right? Why don't I put ones here?
Because it's A prime.
Because it's not A anymore, right? A is just this half. Exactly right. Who was that?
Jordan.
Very good, Jordan. Correct. Okay. Next one, B prime C. B prime C. We got two ones in the middle. However, there was already a one there, right? But that's fine. That happens all the time where, implicants, even prime implicants will, intersect each other, right? But we don't know that these implicants were prime or not. So, but we're not done yet, right? We have one more term, and this is a min term. It'll be a single one. So let's go A prime, B, C prime. Okay, so now we start working. Let's find the biggest implicants here. So first suggestion, the biggest prime implicants with the ones that we have on the K-map. It's a simple K-map, just 3 dimensions.
The bottom 4 ones?
Yeah, that's great. Just easy. So that's a nice big prime implicant. Covers more than half of them already. So we'll call it X. Okay, very good. Any other ones? Any other big ones?
The ones on the left and right side.
That's right. Right, because if you remember, as you remember, this thing connects in the back. And when I say that it connects in the back, it's not no magic, right? It's if the middle thing is C, right? The sides are C prime, and that domain has to be contiguous, right? The idea is that when we're going to be translating into minimal form of a function, right? We're saying, oh, well, C prime will imply all of these ones, right? So, but that is correct. Who was that? Was that Jordan again?
Yeah.
Yeah, okay, good. Excellent. So we could be done at this point, but right, we've covered all ones, but we want to exhaust this thing, right? Any other suggestions?
The center two ones, if we're gonna do Y, then we need those extra two.
Just these two?
Yeah, I guess we can do the full 4, but.
Well, that's the thing, is that if you, I mean, it is some kind of implicant, yes, but it's entirely within another one, right? So we don't want to do that. It's entirely within a bigger implicant, so it's not a prime. It is technically an implicant, but it's not a prime implicant. All right, so we have X and Y, right? And both of them are essential. Why? Because this red is X covers these two ones that the student just mentioned, and nothing else covers them. And then on the other hand, Y covers these two ones in the top corners, and nothing else covers them. So both essential. And now we want to translate them into actual variables or literals of our function, right? So we say that X implies all of B prime, right? And that's the case because there is the B and X covers all of B prime and none of B, right? That means that whether or not A and C are 1 or 0, right? The term is going to be 1, right? So how can I assert that? This prime implicant covers fully A and A prime and intersects it fully, all of it, right? And then it also intersects fully both C and C prime. Okay, very good. And then the other prime implicant, also very big, is entirely within C prime, right? So it doesn't go into C at all and covers the entirety of C prime and intersects fully D and B prime and A and A prime, or not fully, but intersects, covers them, right? Covers A and A prime. So that means that whether or not with this term B and or A are 0 and 1, doesn't matter. This term in the sum is going to be 1 as long as C is 0, right? And same thing with this one. Whether or not A or C are 1 or 0, this term is going to be 1 as long as B is 0, right? Because they're both complements. Any questions about this? And it's just one minimal form. Okay, next. So this is the harder one, right? This is the new one. So how do we quickly go from this representation of the Boolean function to the standard canonical form, right? Standard canonical form has all of these numbers represented as mean terms, right? Each term has all 5 variables. And we know that we need 5 variables because the highest number here is over 15 and less than 31 or less than 32. Okay, so what's the super quick way to go from these numbers to these prime implicants? And there's a couple of ways of going about it, but what's the quickest one? Well, nobody really?
Convert them to binary.
Yes, that's right. Is that Patrick?
Nephew.
Nephew. Okay, it's nephew. Great. That is exactly right. You convert them into binary, but now you should be able to do it in your head. So like 0 is going to be 0, or 5 zeros. And whenever it's a 0, it's a complement. So it's 5 complements. Okay. Then 1 is going to be 0, 0, 0, 1. So it's the same, but E is true value. Then 4 is going to be 0, 0, 1, 0, 0, right? So we have 5 zeros, but 1 in the middle, or 5 complements and 1 true value in the middle. Then we have 5, just 1 more true value, it's the E. Then we have 16, it's going to be 1 and 4 zeros, so A is true value, the rest of them are complements. And we have 17, almost the same, but the last one, the E is now true value. 21 is going to be 16, no 8, 0, 4, 0, and 1. Okay? Then 25 is going to be 16, 8, 0, 0, 1. Then 29 is going to be 16, 8, 4, 0, 1. And when I say 16, I mean the 1 in the first position. Everybody who is uncomfortable with this, just tell me now and I'll go over it. Right, so as Nephew said, you just convert this into binary. You can do it in your head or on paper if you want, and then just all of the zeros become complements and all of the ones become true values, so no prime. Okay, good. So we did that. So now is our scary, 5-dimensional K-map. All right, so let's start putting them on the board. We don't remember where the numbers goes, but that's fine. We can really quickly go, okay, A prime, then B prime. So we already narrowed it down. Then we go C prime, where it intersects them, right? So C prime has, a couple of regions, but the one that intersects is this one we care about. Then we have D prime. Again, you have it on top, but we only care about it here at the bottom. So now we're down to 2 cells, and then E prime. This is E, and this is E prime. So we got the one. And we do it for the rest of them. So for example, 1 is the same, but instead of E prime, it's E. So it's symmetrical, goes there. Then 4, it's actually going to be similar to 0. The difference is that instead of C prime, it's going to be C, right? Then 5 is just one off from 4, right? The difference is that E prime is now going to be E, so it's going to go to the other side. Then the next one is actually similar to 0, right? Instead of 5 zeros, it's 1 and 4 zeros. So only the A is different. So instead of A prime, it's going to be A, right? So sort of symmetrical on the other side here. Like everything else is the same. Then what do we have here? 21. B prime, D prime, what is that similar? I think it's sort of similar to 4, right? Instead of A, we have A prime, then we have B prime, C, D prime. Okay, so a couple of different, but we can sort of, let's say we start from the beginning for 21, right? So we say, okay, A is on either of the sides, okay. B prime in the bottom. C is going to be either here or here. D prime is going to be all the way in the bottom. And E is going to be on the left side. There it goes. And then for 29, looks like the only difference is C here, right? So instead of C prime is going to be in C. Did we get all of them? I think I missed one. Oh, I guess, okay, sorry, I missed 25. Okay, so here we have them. It's 8 ones on the board. Any questions? Okay, so now the hard part starts, right? So that was just straightforward. Now we need to imagine, we need to find the implicants, right? So we need to find groupings of them, but we need to imagine this thing as a 4-dimensional figure 8. I don't know. So
aren't we missing 29?
Right.
no, I got 29. I think it's. Am I missing 29? Oh, I guess I am missing 29. So let's. Yes, thank you. Right, 29 was just one different from 25. Instead of C prime, it was C. Right, so C prime was here, and then C. Everything else is the same. Thank you. Yes. And that was Patrick, right?
Yes, that's correct.
Oh, okay, good. So, I think 6 students are asking me questions and answering them, but there are 30 of us. So just try it, just to practice, okay? Just say something. Okay, didn't mean to do that. So that was an easy implicant, right? I took it away from you, right? 1 and 4 in a row. Yeah.
I have a question. So would like all contiguous subarrays of size 4 on the bottom be groups? Would it work like that? Because then you have like a lot of groups, don't you?
Not all of them, right?
Oh.
So I was going to ask, and that was an easy one, so somebody would have answered it. But what's another easy one? Right, so I got group of 4. Yes.
5, 29, 17, and 21. Is that a grouping?
5, 21.
No, 25, 29, 17, and 21.
Okay, 5, 25, 21.
No,
not 5.
Not 5.
25, 29, 17, 21.
21.
So everything on the left.
Right, that's right, absolutely. Right, and in how? Right, it's because our thing is well, among other things, is a donut, but specifically, what we have, the contiguous part, is the D prime, right? Because D is everything in the middle, and D prime is top and bottom, and they have to connect in the back, right? So I think it's both Anna and I think it was Guy or Thomas. So yes, everybody was right. 25, 29, 17, and 21. Okay, so that's another good big implicant, prime implicant of 4. Any other ones?
5104.
Oops.
I'm sorry. So two people said, so 5104 is correct. And what was the other? It was a question?
Yeah, could you do 16, 17, 21, and 5?
So give me a second. So first, what student said is correct. Who was that?
Nephew.
Yes, good. So there it is, right? Again, so here we're entirely within A, right? So they're obviously connected. It's like a book. And then what was the question you said?
So
Somebody.
16, sorry, 16 on the right, and then wrapping around to the other side, 17, 21, and 5.
So no, because what we
I
would
don't think
get
so
here.
either, but it seems like it should be
Well,
possible.
no, because it's not sort of symmetrical in the sense that what you're doing
Right.
is you're taking here C prime, you're ending with 5. Okay, so the problem is A, like C and C prime is fine, but the problem is with A, you're spanning A prime and A, right? But there is at least one more here. And the one that I'm thinking one of is really hard.
You can do 17, 16, 1, and 0.
I think yes. Yeah, there we go. Yeah, that's excellent. 17, 16, 1, and 0. Was that Anna?
No, this is Chelsea.
Oh, this is Chelsea. Excellent. Chelsea, welcome. And what is it? Hit it out of the ballpark. So we want to hear more from Chelsea. Chelsea, explain. That's crazy what you just said, and it's correct. Like, how did you get that?
Well, it's because you mentioned it wrapping around and being symmetrical. So, since these are like two K maps combined together, the C primes on the end kind of wrap around to be combined together, and then the C prime in the middle kind of connects that like circle.
That's exactly right, and I guess it's less of a well, in some dimension it is circle, but I guess the way we can look at it, it's more like a figure 8.
Yeah.
Like all of these C prime. So well, clearly these two connect, right? They are like sort of like in the middle of the book. But if it's like 2 pages in the book, imagine like bending the other two and like sticking it in there. And that is exactly right, right? It's the contiguous C prime allows us to get that. And I think this is all we have, right? So we have X. So that was actually excellent, Chelsea. That was good that you saw that. So we have X, we have Y, we have Z, and we have the extra special T. Okay. So let's put them on the... Yeah.
Yeah, may I ask, yeah, so what I was saying before about 16, 17, 21, and 5, it's not just that they need to be contiguous in powers of 2, there's more to it. They need to be symmetrical as well.
Well, so, well, symmetrical against something, right? The problem, yeah, yes, the problem with symmetry though is sometimes it's in the eye of the beholder, like symmetrical around what? The good check though is to imagine, because these prime implicants, they need to, in the end, become represented by a product of something, right? And the idea of the prime implicant is that that product, the bigger the implicant, the fewer terms this product should have, right? Okay. So in this case, we have a function of 5 inputs, 5 variables. That means that a single square will be represented by all 5. Like a little implicant of just 2 would be now represented by 4. And these implicants of 4, whatever shape they are, would need to be represented by just 3 variables, okay? And as we'll see in a minute, right, our implicants of 4 will be represented by 3 literals each. Now, in your proposed 16, 17, 21, 5, you know, try to represent it with 3 variables, and you will not be able to do that, right? So I think that is the check. Because I think symmetry is too, you know, vague, but this is a hard check, okay? Okay. So, right? And that is sort of what we just talked about. So it was a great question. So do 16, 17, 21, and 5 create an implicant? Well, we try to express the implicant with variables. It's exactly what they just said, what we're putting it on the slide. And the only way is that the part that does work, right, is that implicant is entirely within B prime, right? That's below the, you know, this equator, and also entirely within D prime, right? Could be top or bottom. In this case, it's bottom. So far so good. But now we need a third one, and there is no third literal into which it entirely falls, right? You could say, oh, how about I don't know, C. So C, no, C prime. How about A? Let's see. So 16, 17, and 21 are A's. So far so good. But then, oh no, 5 is inside A prime, right? So we cannot find the third variable that will fit into that one. Any questions? Yeah.
I have a question. Let's say there was another one next to, like, on the left side of 16, like, do you know what right there? Yeah. Would it be possible for 21, 17, 16, and then that one to be an implicant then?
Yeah, sure, right? Because then they would fall into A, right? So if we didn't have, or whatever, it doesn't matter what we would have here. But if we had, was that Chelsea?
This is Anna.
Okay, good. So yeah, Anna is correct. So if there were a 1 here, then we could have another implicant of 4 that would be this, so whatever, this, 16, 17, and 21. Yeah, and they would.
Wait, couldn't it just be an implicant of 8? The whole.
You could have an implicant of 8. Oh yeah, that's right. Yeah, absolutely. If we had the 1 here, then yeah, we could have a big implicant of 8, which would be awesome, because then we would only need 2 variables, and in fact the variables would be B prime, D prime. So who was that? Jordan, very good. Okay, excellent. Okay, so as it is, without any hypotheticals, we have 4 prime implicants. All are big, all have 4 ones in them. X, Y, Z, and T. Okay, now are all of them essential? Which one is not essential? Which ones are not essential? Which are essential?
They're all essential.
Okay, so was that Guy?
Yes. Sorry.
So Guy said things that they're, or proposes that they're all essential. Any other thoughts?
I think we can do without X, but that's
Oh, we can do without X. Sorry.
Okay, good, right? We can do without x. Why? Well, let's go one by one. So t is essential, right? The crazy one is essential because certainly nothing else covers 16. It didn't mean crazy. The interesting one is essential. Okay, how about y? Yeah, definitely, because nothing else covers 25 and 29. How about z? There's a lot going on here, but nothing else covers 4. How about x? Right, not x, because 17 is covered by t and y. 21 is covered by y. 5 is covered by z. And 1 is covered by t and z. Okay, so x is not essential, as it turns out. But y, z, and t are essential. And now they do cover all ones. I hear somebody's mic. Somebody is typing. And okay, so somebody needs to turn off their mic. Okay, so there they are. The function can be represented by y plus z plus t, and then we will convert them into sum of products of actual inputs. Right, so let's say y, right? It's going to be entirely within A. It's going to be entirely within D prime, and it's going to be entirely on the E side. So there we have it. Then we have Z, which again is, well, not again, entirely within A prime. It's entirely below the equator, that's B prime, and it's entirely in this bottom stripe, which is D prime. And the last one is going to be, let's see, again, entirely below, entirely C prime. So that's the interesting part, right? So this is C prime, and both of these are C prime. And then they're all still in the bottom row, which is D prime. Okay. I'm just, rather than clicking forever, I'll do that. Okay, any questions about this? So something like this will be on the final, probably, right? One of the questions. Yeah.
For the homework, is it okay if we came up with another one, but instead of all of the product parts being 3, like there's one that has 4 terms? Is that okay?
Well, I think it's an okay as an attempt, yeah. And like, if you submitted that, you get credit, no problem, no question about it. So you have also 3 terms. It's a sum of 3 products, but one of your products has 4 literals. Yes, that's what you're saying. So it's, in the end, it's not a minimal form, but as a submission, it's excellent, right? Because I think for many students, they didn't get all the way to the end, right? So you did. So yeah, you got credit. In fact, as I said, as long as you submit the homework, if it's, for that matter, quizzes too, even if they're not perfect, you get credit for them in a sense that the assessments that will bring your grade down are the exams, right? So on those you have to be right. On the exams you have to be correct. Okay. So other questions about our K-maps, including the 5-dimensional ones? Okay, we're not going to do 6 dimensions, but obviously you could. So can somebody guess how we would do a 6-variable K-map? And it's actually not that hard. How could they add one more variable to this K-map?
Can you sorry, go on, please.
Would there be 2 more 4-variable K-maps?
Yeah, or yes. Could the other student say that in different words? Yeah, that's right. There would be, 1 second, you said 2 more, right? There would be 2 more.
Yeah.
Below, yeah, that's what you said. That's correct. But what's another way to say that?
You need 2 to the 6 amount of like possible.
Yes, you need 64 cells. That's right, and you get them by putting 2 more squares below. But those 2 squares,
You double.
you flip them down, right? You imagine this as a mirror, right? And the what's in the bottom is going to be the mirror reflection of what's on top, just like we did with E, right? With E, this was a 4 variable K-map, and we reflected it on the right like a page in a book. With this, the original one became E, and the reflection became E prime. So if we have a variable f, then all of this is going to be f, and then what we flip down, all of that is going to be f prime, but all of the other ones are going to be the same. Okay, but I'm not going to ask you to do that, but it's just, there's no magic about it. Okay, new topic, right? Completely new topic. Now we're going away from the abstract. Well, no, we're not going away, but we're staying with the abstract Boolean algebra, but now we're going to apply it to something very...
Say, Professor, I had a question about the
something very real. Go ahead,
third
question.
option, or the third question from the homework.
Okay. What was that?
It listed in the summation, I think 2 minus 7, and I wasn't sure if that was a typo or something else.
Okay, so this was part of the homework. Okay, let's see.
That was 2 through 7, meaning 2, 3, 4, 5, 6, 7.
Right, this is not a minus, right? It meant a range, I guess. So 2, 3, 4, 5, 6, and 7.
Okay, thank you.
Yep. Okay. Other questions? Yeah, like both of these are, 5-dimensional. And yes, I will open the homework and you can submit it until tomorrow. And I thought that there was a new one, or it's coming. The new homework is coming. Okay. All right. So let's do the cool new topic, where we're going to take these abstract functions and make something real with them. And what we're going to make is called a 7-segment LED display. This is really old school, but you still see them today. Maybe not today, but you'll see them, in September. Where will you see these 7-segment displays in September, right? This is what it looks like. It's basically 7 little, or not so little, LED lights, like linear, and you can use it to display all 10 decimal digits, starting from 0 through 9, right? So we would go for 0, we would have to light up all of them except for 7, right? For 1, we would only light up 2 and 3. For 2, we would light up 1, 2, 7, 5, and 4, right? For 3, we would light up 1, 2, 3, 7, and 4. For 4, we would light up 6, 7, 2, and 3. For 5, 1, 6, 7, 3, 4. For 6, 1, 6, 5, 4, 3, 7. For 7, we would do 1, 2, 3. And for 8, we would light up all of them. And for 9, all of them except 5. Okay, so where have you seen this?
Like in high school scoreboards for sports.
Yeah, high school scoreboard for sports, and more recently?
A clock, I guess.
There's some clocks, yeah. Where all of us saw it a year and a half ago. And we're going to see it again in September. Actually, maybe not. I'm thinking of the North Building elevators, but they actually replaced them, right? Before they refurbished the elevators, do you remember?
I think a
The
lot of us
full-
haven't been on campus
Yeah,
yet.
a lot of us haven't actually been to Hunter yet because of the whole online thing.
Oh, okay. So, all right. Well, you know, in the bad old days, and you'll be on campus in September. It'll be quite something. So, most of your classes with CS majors are going to be in the North Building. Our department is in the North Building, which is a building with at least 10 stories, maybe more. No, more like 15, more like 16. Right, it's a tall building, and there are elevators. There are 4 elevators, and you go. They actually replaced the displays in the elevators recently, but for 30 years, the floor numbers were like this. And back in the day, even like the wristwatches, that's how digits were represented in them. And some of you, maybe your parents have like old alarm clocks or things like that, right? So all of that had a 7-segment display, and then later on they also had 9-segment displays. So same idea, but you also have 2 diagonals like that going from here to here. And you can have a fancier 3. Your 3 could be 1, 2, 3, 4. I don't even know that it's better, right? So anyway, we're going to work on this 7-segment display for decimal digits. Any questions? Yeah, that's quite something for you to start college without actually seeing the anyway, it's strange times. So each segment lights up when the digit we want to create requires it. We will focus on the segments and write one function for each of the 7 segments. So, right, so for example, we would have a function for segment, I don't know, 1, 2, 3. And so for each segment, so each segment will have its own Boolean function, meaning that in a particular situation, that segment, its value is going to be 1. The function, the f, 1 is going to be equal 1 whenever 1 is required, and it's going to be 0 when 1 is not required. So just as an example, we can look at 2 of the functions for 6 and for 7. But of course, there has to be a function for 1, for 2, for 3, for 4, for 5 also. Notice, and this is convention, there is no specific reason for it, but as a convention, when we show, let's say, minimal forms or just have a number of Boolean functions, just conventionally, or maybe the way I like it, we start counting from 1, right? But it doesn't mean anything. We could be starting counting from 0, but right. So anyway, so let's look at LED 6 and LED 7. So for any function, the segment could be either off with a 0 or on, right? Fi with 1. And here we have a table of our decimal digits, 0 through 9, and the inputs that will represent it, right? And it looks like I have 4 inputs here, x, y, z, and t. Why do I have 4? Why not 3? Because like 0 can be just represented with 3, or rather 1 can be represented with 3, 2. Why 4? Why not 3? Why not 5? Well, as in the very beginning, right, we represent our decimal digits with binary numbers, right? Because we were converting from from decimal to binary, right, to octal to hexadecimal. So in this case, we need binary, right? We're working with Boolean algebra with just two sets, 0 and 1, right? And then if we convert the digits, decimal digits, into binary, right, we can convert 0 through 7 using just 3 bits. But to have 8 and 9, we need 4 bits, right? So we're going to use 4 bits for all of them. And then just as it is, 0 is 0, 1 is 1, 2 is 10, 3 is 11, 4 is 100, right? 8 is 1000, 9 is 1001 in binary, right? Any questions? Right, so we just look at the binary representation of the 10 decimal digits, 0 through 9. And we need 4 binary digits to represent all of them. And each binary digit will become a variable or an input in our function. Right, and we're starting with looking at function 6. Right, it's the function that represents the behavior of LED number 6. So this is, we're talking about a real circuit with like real parts that light up. Any comments on this, what I have here? I would make at least one comment. Anyone?
I don't even know what to ask, but I'm kind of confused. Like, can you go like over it again?
Starting from where?
Like what so like each of these tables is for like one of the lights?
So for one of these little lights, let's look at this one. It's a thick red line. What we need for this is a circuit that is equivalent to a function, right? And that function in the end could either be 1 or 0. So when 1, this little stick is lit up, and when it's 0, it's not lit up, right? And we're going to represent the behavior of this function in this column, right? It says column F6. And it's going to be the result, this function is going to be the result of the 4 inputs, right? Just like all of the functions that we looked at in chapter 3 so far. We're starting with the 3 light switches problem. We've been looking at Boolean functions with multiple inputs, right? With multiple variables. And when we were looking at the 4 different standard forms and canonical forms and minimal forms, we were simplifying these functions as much as possible so that given different combinations of 4 inputs, we can produce the predictable behavior with the 1s and 0s, right? So now the purpose of this function F6, now it has a real purpose, is to make sure that this one stick LED lights up only when we need it to represent a decimal digit, right? So for example, if we have digit 5, we want this, 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 and this to light up. So for, let's say, decimal digit 5, we need F6 to light up. That means that if we look at 5, right, that's decimal 5, we now look at its binary representation, right? Decimal 5 is binary 101. Why? Because this is 1s, we have 1, we have no 2s, and we have a 4, and we have no 8s. Right, or we can just basically, it's 4 plus 1 is 5, right? So this is the binary representation for 5. And this binary representation, for each binary digit, we have an input. And each binary digit can be, either 1 or 0. And, T represents 1s, Z represents 2s, Y represents 4s, and X represents 8s. Right, and in order to make up a 5, We need the complement of x, which is 0. And then we need the true value of y, which is 1. We have a complement of z, which is 0, and a true value of t, which is 1. And behavior that we're charging here of f6 should be such that with these 4 inputs, f6 should be what, Stephanie? Should it be 1 or 0?
It should be 1.
Excellent. It should be 1, right? And then, for example, with, let's see, how about let's pick a different number. Let's pick 3. So for 3, decimal digit 3, we need this one to light up, this one, this one, this one, and this one, right? If I want to represent 3 on this display, will 6 light up or not? Anyone?
No, it won't.
No, 6 will not light up. So we need our function for this LED to not light up when I have decimal 3. So here is decimal 3 represented by, well, in binary as 11, right? 0 8s, 0 4s, 1, 2, and 1, 1. And then with variables, it's going to be complement of x, complement of y, true value of z, and true value of t. And what should the behavior here be in F6?
It should be 0.
Should be 0, right? So, I mean, that's it, right? We want to just fill this column with 0s and 1s. And then we're going to do that together right now. And then for homework, you're going to do the same thing for function 7. And if you want to practice, you can do it for the rest of them. So in order to complete this table, right, we would have F1, F2, F3, F4, F5, F6, and F7, right? But, you know, it will be, you know, too much of the same. All right, so let's do F6. Right, so for 0, we need all of them except for 7, but we're looking at 6 specifically, so it should be 1, right? For 1, should be 0, right, because just 2 and 3. For 2, again, no 6, 0. For 3, no 6, 0, as we just determined. For 4, yeah, we need 6, 7, 2, and 3, so should be 1. For 5, yep, should be 1. For 6, should be 1 again. How about 7? For 7, should it be 1 or 0?
0.
0, yeah, because 7 doesn't require that LED. And for 8, we need all of them, including 6, so it should be 1. For 9, also we need the 6, so on. And we're done here, right? So I'll ask that question again that I asked 5 minutes ago. Any comments? Any sort of like musings that you get at this point looking at this table, right? You know, any thoughts?
I just not like, I guess just thoughts. This topic feels pretty good. Like it's a good build up off of everything else, and it feels pretty simple to understand how you explained it.
Good. Is this Mohammed?
Yeah, this is Mohammed.
Okay, good. Yeah, it definitely feels good to me. But you know what? There is something, if we look at slightly bigger picture, it'll feel even better. So what I'm thinking is with a 4-digit binary number, yeah, we can nicely represent decimal digits 0 through 9. But can we represent more than that with 4 binary digits?
No, you
Yes.
can't. Oh, really? Oh, sorry. No, I thought you meant from 0 to 9. Can you represent more than that? My bad.
No, it's fine. But there was another student. What was your thought?
You can represent more than 9 digits with binary. You can represent up to 16.
Yeah. Is that nephew?
Yeah.
Okay. Yeah, right. Obviously, we don't need the other 6 representations, right? They're, sort of useless to us. But yes, these are possible combinations of inputs, right? You could have X, Y, Z, and T, all, lit up with, or all having, juice going, electricity going through them, and that would be, and that would be the equivalent of decimal 15. But, obviously, there is no decimal. Like if we had a hexadecimal elevator, then yes, but well, actually no, we couldn't do that because our single-digit 7-segment display can only, physically cannot do that, right? So when we are charting our function, function 6, right, its behavior has to be predictable with these 10 various combinations of inputs of X, Y, Z, and T, right? So, let's say when when all of them are, dead, when no electricity is going in for X, Y, Z, and T, when they're all complements, the function has to be 1, right? Because it's representing the digit 0 and it needs 6, right? It needs the segment 6. And then when it's 1, the segment 6 has to be 0, right? So for our function 6, with these 10 possible input combinations of the 4 variables, this has to be the outcome, right? 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, right? This is what it has to be. How should this function behave with these other 6 combinations?
Oh, wait. I have a question. Why is 4 1?
Why is 4 1? So there is the little 4. It's in red. So you tell me, why is 4 1? Is that Jordan? Is that Jordan? Or
No. That was Nafi asking the question, and
okay,
I think
Nafi,
someone else was answering.
Can you say that again?
I think someone else was about to answer.
Go ahead.
Yeah. I was going to say that like F6 and 4, you can see it on the tiny red 4 that's next to the 4. The left segment there is lit up as red, and that's what F6 is supposed to represent.
Nephew, does that make sense?
Oh, okay. Yeah, I see.
Right,
Okay.
we're actually building this thing.
Yeah, it's like a clock. Yeah.
Yeah, we're like, our functions so far were like purely abstract, and now they're becoming concrete. We're building this thing. Okay, good. So my question is, if the behavior of function 6 has to be absolutely determined for the 10 input combinations, right, from 0 through 9, what should it be for the other 6 possible input combinations? What should the outcome be for function 6? Anyone?
Wouldn't we be using 2 LED, like 7-segment LEDs instead of just 1?
Yeah, that's right. If we needed to represent, if our building had more than 9 whatever stories, in the basement or whatever, then we would need 2 7-segment displays, right? All the way up to, I don't know, Empire State Building or whatever. If you have up to 99 floors, then yeah, you would just have 7-segment displays, and that would be fine. But we don't. We have a single 7-segment display, right? Our building is not too high, and again, I repeat my question. The actual device will have the 4 wires going into it, and there are actually 16 different combinations of on and off electricity going into those 4 wires. So, and again, we see that the behavior of this function, the outcome, has to be exactly like this for the first 10 combinations. But what about the last 6 combinations, right? What should I fill these 6 squares with?
Can we just fill them with zeros?
I could fill them with zeros, yeah. Could I fill them with anything else? Could I fill them with ones? I don't know. Could I?
Won't you, um, this is just a guess, but won't you just basically do the same thing as in the top part because it's the same numbers? Like 10 is going to be the same as 0 because you're using a 0 and a 10, and then like for 15 you're using a 5.
Okay. So proposal is that after 9 I just repeat the first 6 or whatever. So the proposal is to fill it with 1 0 0 0 1 1. Could that be okay?
Well, doesn't it depend which digit it's trying to represent? Because if we're doing the tens place digit, then they would all be 0. But if it's the ones, then it would just be the copy of what we have above.
So Patrick says that it doesn't depend. Can you say that in other words? Well, it doesn't something. What does it? What does it not do? So what? Yeah.
I think I'm a little confused about what you're asking.
Well, look, this function, right? It's going to, or rather, this LED, right? The actual LED, the actual light up part, depending on the 4 wires, whether or not there is electricity in any of them or all of them or any combination of them, it will either light up or not, right? Just like physically, it will be in either of the 2 states, right? And this is what it has to be with the 4 with the first 10 combinations of these inputs, right? This is what will happen. So for example, when the first 2 wires are dead and the last two wires are live, this LED has to be on, right? And when the first wire is dead, the second is live, this third and the fourth are dead, it has to be on, right? When the first wire is dead and the other 3 are live, has to be off, right? So the actual behavior, it has to be, this is how it has to be. And then what if I have the first wire live, the second dead, the third one live, the fourth one dead? What is it going to be? Is it going to be on or off? Or I don't know, what if all 4 wires are live? Is it going to be on or off? Right?
If we're thinking about normal digital clocks, I feel like when they aren't showing a time, it's all lit up, so they're all ones.
It's all lit up. Why would it be all lit up?
Just like if we're looking at a digital clock, if that's what this is representing, when it's not showing a time, generally they just, all the light bars are on. It just shows 8.
Well, so you're describing a situation where the clock is not functioning. So let's not worry about that. Let's only worry about situation when the clock is functioning, when it's not broken, when everything is fine. And when everything is fine, yeah. It's not a trick question. The answer is simple. Go ahead.
So I guess I have a question. So for the 10s for the 10 to 15, right? Will it be representing the ones or the 10s place? Is that a stupid question? I don't know.
It's not a stupid question. It's a great question. And the answer is that it's not going to be representing anything, right? It's not representing anything because the only things that need to be represented is 0 through 9, because in the normally functional clock or elevator or whatever, these are the only 10 possibilities, right, that need to be represented. Nothing else needs to be represented. Nothing else can be represented, right? So these are the only things that we care about, right? So I ask you again, what should the outcome of this function be with these possible inputs?
Are you, I don't know, I might be wrong, but are you trying to get us to say that it doesn't matter?
Yes, that's what I'm trying to, exactly.
Okay.
It doesn't matter, or in other words, to say it, we don't care, right? So we literally don't care how this function will behave for these 6 combinations of inputs, right? We care about how it behaves here above the double line, and we do not care how it behaves below the double line. Good. Right, in the normal functioning of the clock, it should never occur, right? And that is why we don't care how it would behave if it did occur, right? Because it's a completely hypothetical, it will never occur. So when we're coming up with a function, we're going to come up with it in such a way that we really don't care how it behaves, all right? Right, so do we care about the values that 6 gets for those 6 combinations of inputs? We do not, no, we don't care. Therefore, we don't give value of 1 and 0 for these inputs, right? Instead, we can just say D for like don't care, don't care, don't care, don't care 6 times. Now, these D's we will use to our advantage when minimizing the function, right? Because we don't care about this input, we may be able to make fewer products and make each product with fewer literals. And why is that a good thing?
I mean, in terms of, it would just take up less memory at scale. Or I guess it would just make things more efficient.
You're definitely on the right track, and it will get things more efficient. That's absolutely correct. That is 100% true. As far as less memory, it will not take less memory, right? It's still 4 bits, right? So not less memory, but definitely efficient. Why is it going to be more efficient? Or in what sense? Because remember, we're building an actual circuit based on this function. And when we're coming up with a minimal form, we could build a circuit with the canonical form, right? With like all of the minterms, each minterm has all of the literals. Why are we even minimizing it? What's the point of minimizing these functions before we start building a circuit based on the function?
Well, I guess we're doing it because we don't want to use like bits that we're never going to end up using. So we do that first. We minimize first because we want to make sure that we don't, I guess, make a circuit that utilizes 10 to 15 because we'll never use it, and that's why we're doing this first.
Well, you're right. It's not why we're doing it. It's why we can do this. Yeah, you're absolutely right. We can do this. We are going to do it. But why is that good? And the student who said before that it's going to be more efficient is right. It will be more efficient in more than one way. But why? How? And I'm talking about in terms of actually building a real thing and then running it.
Is it because you don't have to take into consideration the rest of the numbers? You're only doing 0 through 9 and you're not caring about 10 to 15. It's just, it's less terms to consider when minimizing?
Okay, so you said first what the previous student said, and it's true that this is why we can do it. But then the last thing you said is that, which is also true, that is, we will. How about think of it, like what does efficient mean? Efficient could mean in terms of time, could mean in terms of money. how is it going to be more efficient in that sense? Right? And with time, it could be time when it runs. It has when you're in the elevator and it runs faster, or also it takes less time to make it, maybe less money to make it. Will this have that effect?
Well, I would assume that the runtime would be better
Why?
because
How?
we aren't utilizing 10 to 15. So I was just thinking,
Well,
in
okay.
my mind,
So
if you have
well,
15 options, yeah.
everybody said yes. You like the two previous students said the same thing, and it's true. And this is why we can minimize the function. But why is it imperative to minimize the function? Why a function? Why a form of a function that has, like all of the functions are going to be minimal forms are going to be sums of products, right? So when we minimize the function, we make it so that there are as few products as possible in the sum, and then within each product, as few literals as possible, right? So in some cases, we're able to minimize function to just like, I don't know, just a product of 3 single literals, right? So why is it imperative to minimize these functions as much as possible, right? Because they are equivalent to the, say, the longest canonical form with all min terms.
Well, it reduces the amount of like physical circuitry we have to build, right?
Yeah, absolutely. Like when the function is short, it's easier to build it in a circuit, right? Because a circuit will have fewer gates, like fewer things, and fewer wires, right? And you know, when we reduce it as much as we can, we make it as simple as we can. It's easier to make with fewer parts. And then when we're talking about gates, right? In addition to how many total gates, how many different kinds of gates, we're also considered, and this is, we covered this, so it's going to be on the exam, right? So we're also worried about the level of cascading gates, meaning that, you know, let's say that I have 10 AND gates all going into a single OR gate, right? So we just have 2 levels of cascade, 1, 2, and like the 10 AND gates will happen at the same time, and then the other one will happen after that. Whereas we could say have just 3 gates, like and, or, and then another and, right? So it's cheaper to make, there are fewer gates, but they're in 3 levels of cascade, so it's actually going to run a little longer, a little slower. Does this make sense? So because we don't care about the outcome with these 4 possible input combinations, that bodes well for us to be able to minimize this function further, right? And although it will still take 4 bits of memory, that's fine. Our circuit is going to be simpler and faster and cheaper to make, and faster to make because of that. Okay, so this is the answer. All right, so again, these D's we will use to our advantage when minimizing the function. The function we create will have to give a value of 0 or 1 for every possible input occurring or not. So in the end, the function will behave in a deterministic way. Let's say that we simplify it all the way to the most minimal version because of this. I don't know what's happening. And even though we don't care, in the end, our minimal form will produce 1s or 0s in each of these cells, and they will be deterministic. It's just we don't care what they are, okay? So whether the value in any of these 6 cells will be 1 or 0 will be established so that the function gets the minimal form, right? So, or once we get the minimal form, yes, there will be some determined outcomes, but we don't care what they are. Right, so let's just put these in there. I don't know what it was doing just before, but okay. Any questions right now? Okay, no questions. guess this is all. Did I go too fast? No, I guess we have about 10 minutes. Right, so tomorrow I'm going to pick up from this, and I'm going to show you how we're going to take this advantage. And here, what I have is when we, put the 6Ds there, we're dismissing 2 to the power of 6 possibilities here, right? So we're minimizing this function 2 to the power of 6, where we're looking at 2 to the power of 6 possible combinations, which is 64 combinations, and we don't care about them or something like that, right? So we put these Ds on the K-map. Oh, okay. So the last thing, the way the slide comes out, the last thing, and I thought like, yeah, I really need to tell you now. Okay. So there are 64 different possibilities for D being either 0 or 1, right? So we minimize 2 to the power of 6 or 64 functions at once, right? We put the Ds on the K-map. We can either put them with 1s or 0s, right? So what I want to, what this means is this, right? The fact that we don't care about the outcomes here means that this function f6 could actually be different functions, right? There could be one version of that with the D with a 0 here, or it could be another version with 1 here, and then same thing goes for all 6 of these, right? So in fact, what function 6 is going to be, it could be any of 64 possible functions. Does that make sense? If it doesn't make sense, tell me, right? So what the slide says is that we can have a function f6 that has, outcomes of 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, and then 1, 0, 0, 0, 0. And then we can have another function that would also satisfy a requirement that would start the same, but have 0 here. And then we can have another possible one where it has 0 and 1 here, right? And in fact, there are 64 possible functions that would all work as our f6. Okay, so somebody started saying, go ahead.
So basically, when we put this on the Karnuagh map, then we can just, with all the Ds, we can use them to make the most efficient kind of implicants, because they can be whatever we want them to be. So we can like make a group of 4 if there's a D there, and we only have 3 otherwise.
That is correct, right? So what we're going to be doing tomorrow is we're going to be putting this on the K-map, and then because so many cells can be either 1 or 0, we can say, oh, in order to build this huge prime implicant, with, I don't know, 8 1s, I'll just say that all of these Ds, I'll count all of these as 1s, right? And because I don't need these, I'll count them as 0s, right? Because when we are working with a completely determined K-map, our hands are tied. We need to cover every single one. And because of that, some of our implicants are little. Yeah, and then also when we do the big implicants, we can't make them too big because it has to be, sort of like a, some kind of rectangle of all ones, right? But now, when we're going to have, a bunch of these Ds, then at will we can change them between 1 and 0. We'll be able to make really big prime implicants, and not too many of them. Like we will just have few prime implicants, which translates into very few devices on the circuit board, or very few gates, right? So that's exactly right. So again, we can put them on the K-map as we wish, as 1s or 0s. Whether that value will be 0 or 1 will be established so that the function gets the most minimal form, right? The absolutely simplest possible minimal form. And we're going to do that tomorrow. Any questions about any of this, right? We'll keep working on it tomorrow. Any questions of anything so far with like the quiz and the homeworks? I think the quizzes was pretty much exactly like, the homeworks. Yeah, any of the students that we don't hear from, do you guys have any questions? Okay, so the homework is to build outcomes or just fill in out. It's a small homework, right? So I want you to finish the homework from yesterday, and the new homework is like really, you can do it super quickly, to build F7. And if you want to practice, you can do like F1, F2, right? So, for this table to be truly complete, it would need to have 10 functions, F1 through, I'm sorry, I'm sorry, what am I saying? It will have 7 functions, right? Each function, not for each number, but for each LED, light emitting diode in the display, right? So we will need a total of 7 functions, right? So the required homework is just to do function 7 for this one, right? What are some of the devices that you may have at home that have these light emitting diodes? They're not like that. They're, well, smaller and there's more of them, but do any of you have like a big device at home that has a lot of these LEDs, light emitting diodes? That's the last question for today.
We have clocks on ovens or microwaves and stuff.
Oh yeah, for sure. Microwave clocks. Yeah, exactly. That's for sure. The microwave clocks actually have these 7-segment displays, right? But there are other devices that have not 7, but I don't know, 1 million LEDs or 2 million LEDs or.
Oh yeah, like screens, computers,
Yeah,
TVs,
right.
etc.
Like a lot of your TV sets are LEDs, right? And they're not like lined; they're like little dots, and they're behind. So the actually no, with millions I went overboard. So most TV sets use LEDs as backlight, and there are not as many of them as the pixels, right? And then like some of you have like really new fancy TVs that they have zones, right? Or the less expensive TVs are edge lit, and the more expensive ones have like brightness zones. And the more zones, the better they are. And they sell them as mini LED TVs that may have about 100 zones, and the micro LED TVs that have maybe 1,000 zones. And then some of the more new technology that is prohibitively expensive. It's like an LED wall where each pixel, right, is its own LED, or even several for the 3 color channels. So that's and for example, some of the Samsung and iPhones have organic LED screens, right, where the light emitting diodes, there is one for each pixel, right? Anyway, so it's the same same thing, but miniaturized and better. But anyway, so that's all for today, and I'll see you tomorrow. Okay?
Thank you, Professor.
Thank you.
Bye.